This video goes over a few preliminary questions before jumping into sp3, sp2, and sp hybridized orbitals, and how to determine which one to use. How sigma and pi bonds work with single, double, and triple bonds, hybridized orbital diagrams, as well as a detailed explanation of an exception that is often passed over too quickly, leaving students confused. I explain using Lewis structures and 3D models I designed to better help you see the full picture. Please take a moment to like and subscribe to a free tutor, and let's get started with those preliminary questions, starting with, what is getting hybridized here? The atomic orbitals are what is getting hybridized. Each non-metal atom that we will be talking about will have 4 orbitals. It will have 3p and 1 s orbital. For the p orbitals, remember that they are shaped like a propeller. This green one has 2 ends, but it's still 1 orbital. This blue one, again, is 1 orbital, and this pinkish purplish one is 1 orbital. The x, y, and z are just showing that they are all perpendicular to each other. The last question we need to cover before hybridizing is, how many electrons can an orbital hold? You may be familiar with these diagrams that show half arrows representing an electron. Each line represents an orbital, and each orbital holds 2 arrows, one up and one down, like this. So an orbital holds a maximum of 2 electrons each. Let's show these on our 3D model. We have our S and we have our 3 Ps. Note again that both lobes are 1 orbital, and they each can only hold up to 2 electrons. Now moving on to the 3 kinds of hybridization. When orbitals hybridize, they keep the same number of orbitals. 4 orbitals that are shown here, 1s and the 3p orbitals, become 4 sp3 orbitals. It's called sp3 because it takes 1s and 3 p's, becoming 4 sp3s. Note, 4 orbitals became the 4 orbitals pictured here in this 3D model. Each of the hybridized orbitals will try to be as far from the other 3 orbitals as possible. This angle is 109.5 degrees, and the geometry is called tetrahedral. The second type of hybridization we're going to talk about is if you only need 3 hybridized orbitals instead of 4. And we will get to the whys of how many orbitals you need in a little bit. But if we only need 3 hybridized orbitals, we will use the s orbital and only 2 of the p's, creating 3 sp2 hybridized orbitals. As shown before, 1 s and 2 p's make 3 sp2 hybridized orbitals. One of the p's will remain as a p orbital. In my 3D model example, you see that p here. Now that there's only 3 hybridized orbitals, with them trying to get as far away from each other as possible, the degree is going to be 120 degrees from each other. They will be planar, or all on the same plane, or flat, and thus called trigonal planar. The third and last type of hybridization we're going to talk about is if you only need 2 hybridized orbitals. We would use the s and 1 p, and that would create 2 sp orbitals. Again, the s orbital and 1 of the p's would be used to make these 2 sp orbitals. The last 2 p's will remain unhybridized. In the 3D model example here, they are here and here. The sp orbitals would be as far apart from each other as they can be, making them 180 degrees, also known as linear. Let's come back to the question, which of those 3 hybridizations do I choose? Or how many hybridized orbitals do we need? 2, 3, or 4? Essentially, whichever atom we are wondering its hybridization, we count how many things are around it, both atoms and lone pairs. There is an odd exception I will explain at the end, so stay tuned in until the end. But focusing on how things go normally, let's use the molecule H2O as an example. We will determine the hybridization of the oxygen. It has 1, 2 hydrogens, and then 3, 4 for its lone pairs. There are 4 things, which means we need 4 hybridized orbitals. We will use the s in all 3 p's to make 4 sp3 orbitals. 2 of the sp3 orbitals will be bonded to hydrogens, And the other two hybridized orbitals will hold the lone pairs. Those are the dots. And note that the hydrogens will remain as spherical s orbitals because hydrogens can't hybridize since they don't have any p orbitals. They only have that one s orbital. Now let's take a look at CO2. We will find out the hybridization of this first oxygen. It only has one atom around it, and note we are counting the atoms, not the lines. I will not be counting the carbon twice, even though it has a double bond. So that's one. The oxygen also has two lone pairs. That's 2, 3. There are three things around the oxygen. It will hybridize 3 orbitals into sp2 and leave a p orbital like this. The two lone pairs of the oxygen we will put into 2 of the hybridized orbitals, and then the last hybridized orbital is where it's going to connect to the carbon, just like in the Lewis structure. Continuing with our CO2, let's find out the hybridization of the carbon. It has an oxygen on either side and no lone pairs, so that's just 1, 2. There are 2 things around the carbon. It will hybridize 2 orbitals into sp and leave 2 p orbitals like this. Both of these sp orbitals will be bonded to the oxygens on either side, just like, again, the Lewis structure. The second oxygen is essentially identical to the first. It has 3 things as before and is therefore sp2 hybridized. I simply have it in a different orientation than the first, and you'll see why in a minute, but it will still have the 2 lone pairs and the connection to that carbon. When we connect all 3 atoms together, they are connected at their hybridized orbitals. This is an sp2-sp orbital overlap, and this is an sp-sp2 orbital overlap. It's the same thing. You could turn it around and it'll be the same. Where 2 orbitals overlap head-on, it's called a sigma bond. Now I want you to note that the 2 blue p orbitals are lined up, and the 2 green p orbitals are lined up, which is why I switched the orientation of that second O. This allows these p orbitals to overlap at their sides to form pi bonds. 1 sigma and 1 pi bond make a double bond, as shown by the 2 lines in the Lewis structure that we are accustomed to drawing. Before talking about the exception to the hybridization rules that I've been leading up to, we first need to quickly go over single, double, and triple bonds, as far as sigma and pi bonds go. Every bond, whether it's single, double, or triple, has 1 sigma bond. Every single one of them only has 1 sigma. For a single bond, that's all it has, is 1 sigma. In a Lewis structure, one line, as you know, is a single bond, and it represents a sigma bond. In 3D, it would look like this. The head-to-head overlap of 2, usually hybridized orbitals, is this sigma bond. Double bonds have a sigma bond as well as a pi bond. The 2 lines in a Lewis structure represent the 1 sigma and the 1 pi bond. In 3D, you would have the head-to-head overlap, just like before, and then this p orbital and this p orbital will overlap to form the pi bond. Note that even though it overlaps at 2 sides, it's still only 1 pi bond. Triple bonds have a sigma bond as well as 2 pi bonds. The 3 lines in a Lewis structure represent the 1 sigma bond and the 2 pi bonds. In 3D, you would have the head-to-head overlap just like before, a sigma bond, and then these p orbitals and these p orbitals will overlap to form a pi bond each. Okay, now if you feel that that all makes sense, let's talk about this exception. It's actually simpler than you think. Let's figure out the hybridization of each oxygen in this molecule to start. The first oxygen is bonded to a carbon and 2 lone pairs, so it would be sp2 hybridized. This next oxygen is bonded to 2 carbons and 2 lone pairs, so it would be sp3. The third oxygen is very similar to the second one. It has 2 lone pairs and is bonded to 2 carbons, so we would normally think that it would be sp3 as well. However, it is actually sp2 hybridized. This is because you have a lone pair adjacent or one away from a pi bond. In this case, it's a double bond. Let's talk about this rule. It doesn't matter whether it is a nitrogen, carbon, or an oxygen. What does matter is that you have an atom with a lone pair. And that needs to be adjacent or one away from or next to, whatever word you want to use, to a pi bond. In this case, I put double bonds every time, but if you remember from earlier in the video, a pi bond is in a double bond and in a triple bond. Now, when this happens, where you have a lone pair next to a pi bond, you end up with one less hybridized orbital. The electrons are going to be going, instead of in a hybridized orbital, it will be going into a p orbital. So let's take a look here. These ones, all three of them, normally would have been sp3. But since they have a lone pair adjacent to a pi bond, they will be one less, which is sp2. Note that adjacent to a double bond does not mean part of a double bond. If your atom with the lone pair is part of a double bond, as in this case, it will follow regular rules. This one will be sp2 simply because it only has three things around it. As this may come up, let's explain through orbital diagrams. The atomic orbital diagram for the middle oxygen here would be as follows. It will have 6 electrons, and that will fill from the bottom. So we'll have 1, 2 in the S, and then 1 in each of the P's, and then your last one will fill in one of the P's. So that's going to be the same atomic orbital diagram for any oxygen that is neutral. However, atomic orbital diagram is not how it is when it's hybridized. So when it hybridizes, it's going to hybridize, in this case, into sp3. We've talked about that. And so there will be 4 sp3 orbitals, and we'll still have the same 6 valence electrons. So let's fill them in, 1 in each, and then the last 2 will double up. One of these is going to be a lone pair, the other one's the other lone pair, and then one is going to be a bond to carbon on that side and one to carbon on the other side. You can see in this 3D model that the oxygen in red and the carbons on either side are each tetrahedral, and the lone pairs for the oxygen are in the hybridized orbitals. For that first sp2 oxygen, the atomic orbital will be exactly the same as before. All neutral oxygens will be. It's the hybridized orbitals that are going to be different. So since this one is sp2 hybridized, it's going to have those 3 sp2 and then the 1 p orbital. And it will still have the 6 electrons. We'll fill in 1 for each. And then those 2 paired up ones are going to be in your hybridized orbitals. So these are your lone pairs. And then the last hybridized orbital will be your sigma bond to carbon. And your p, that one up there in the p, will be your pi bond to carbon. So remember, double bond takes a sigma and a pi. And notice any of the bonding orbitals will only have 1 electron. The color only goes halfway because I'm trying to indicate that the carbon is providing the other 2 electrons. In the 3D model, the red oxygen and this gray carbon are planar to each other. They're flat. They're in the same plane with their p's perpendicular to that, allowing them to expand and form that pi bond. And notice again that the lone pairs are in those hybridized orbitals. For our exception oxygen, the one with lone pairs next to that double bond, the atomic orbitals will be the same as the last 2. It will even hybridize the sp2 just like the last one. However, those 6 electrons will be going in different spots. As we fill in 1 in each one of the lone pairs is actually going to be in the p orbital instead of in the hybridized orbitals. One of these lone pairs is hybridized and one is in the p orbital. Our other 2 hybridized orbitals will be our connections to a carbon on either side. In the 3D model, you see that the red oxygen and the 2 carbons to the left in gray are all in the same plane with their green p orbitals aligned so they can overlap. The one set of lone pairs is in the p orbital, and this allows for resonance, which I will explain further using p orbitals in another video. I will post that video here when it is ready.